Thank you all for attending. Today I want to share some work-in-progress thoughts on compositional and secure compilation and a new approach to modeling a compiler that I think solves a key problem. So I've been thinking a lot about language interoperability lately, and it has me very annoyed. I'm annoyed because I'm pretty sure that language interop is the problem for compositional and secure compilation. It's the really hard part. If you can solve it, then you can probably develop a compositionally correct and secure compiler. Here's the idea. So when modeling a compositionally correct compiler, we need to define linking between the source and the target language. That is, we may want to link a source component directly with a target component that doesn't have a way to be expressed in the source language. And we want that to be well-defined and covered by our correctness theorem. So think about modeling FFI calls from Java to C. This is most interesting when the target language can be more expressive than the source language. So there are some features that can't be directly expressed in the source. Now for secure compilation, we have a similar problem. We want to enable a target attacker to link directly with the source program and know that we still have security guarantees. So this is most interesting when the target language can make additional observations compared to the source language. In each of these cases, direct interoperability between the source and the target language is key. So what's the right way to model language interoperability? Well, the problem is there are many answers, and all of them are obnoxious to work with. So just off the top of my head, these are a few of the techniques I've seen as contributions in the compositional and secure compilation literature. We have trace semantics, interaction semantics, parametric interlanguage simulations. Each of these is a technique that abstracts the details of the source and target language to enable compositional reasoning between source and target components. Now, they have their pros and cons, but all of them have one thing in common. They all require some duplication of semantics. We start out with our source and target semantics, and we end up duplicating some of those semantics in whatever semantic technique we're using to model interoperability. Since we have two versions of our semantics, we have to show that they coincide. Once we've done this, the proofs are relatively straightforward because we have this single common semantic framework we can do all of our compositionality proofs in. Now there's one technique that breaks this rule, and this one's my favorite. So this is multi-language semantics. This provides a semantics that enables compositional reasoning about interoperability between two languages, but it does so without abstracting the details of the source and target. And in fact, it reuses the source and target semantics. So the key here is that if we start from an operational semantics, we embed those into a common new operational multi-language semantics, and then we define a few new reduction rules at the boundaries between languages in order to define interoperability. So to make that concrete, suppose I have my blue source language and my red target language. They have their own reduction rules already defined, their own semantics, and we want to define interoperability between them. So we essentially embed them into a common new multi-language, and we define these multi-language boundaries. So this TS boundary represents a target term. It needs to behave as a target term, but it's actually implemented internally by a source term. So it's T, it's target on the outside, but S on the inside. So in this case, I have this source lambda, the source function that needs to behave like a target function. So we implement some reduction rules to implement that interoperability. So here I have a source function needs to behave like a target term. So I translate it, I do a little bit of translation, producing a target function, a red lambda, and I move the boundary inside. So I don't know what E is yet, so I just leave that boundary in place. If it's ever used, it will also get implemented in terms of the target language. So you can think of this as anytime we need to use one term in the other language, we do a little bit of translation. So this is great. This reuses our source and target semantics. We just define the interoperability rules. There is no duplication unless we want to use this to model compilation. So when we model a compiler, we end up defining a compiler, a translation from source to target syntax. And we have to show that that compiler respects these interoperability rules. This is pretty frustrating since our operational semantics are very syntactic. You saw the rules, where our interoperability rules look almost identical to a compiler. They're translating source syntax to target syntax. And it gets even worse if you look at some real examples. So this example is taken from Jamie Perconti and Amal Ahmed's verifying an open compiler using multi-language semantics. And it's a very representative example of the problem. So on the top, I have one of the interoperability rules, and on the bottom, I have one of the rules from the compiler. So it's not terribly important what this compiler is doing. I'm just going to walk you through how parallel these rules are. So in both cases, we have a source function. So the interoperability rule has a value of function type in the source language, needs to behave like a target term. The compiler has the syntax of a source function, and it needs to translate that into whatever the target uses for functions. Now, this pass is performing closure conversion. So it's producing a closure, a pair of the closed function and all of the function's free variables as a data structure. A data structure is represented by pack. So the interoperability rule generates a pack statement. The compiler generates a pack statement. They need to generate the closed version of this code. So in the interoperability rule, we generate this red lambda that does some stuff on the inside. We haven't fully translated everything, so you can see a blue term with some language boundaries around it. And that represents the closed version of this code. In the compiler, we fully translate everything, so we generate a red lambda, but there are no blue terms on the inside. We've just fully translated everything. So a small difference there, but in both cases, we're generating a red lambda that represents the closed code. Then we need to generate the environment. So in the compiler, we do this by calculating the set of all free variables, packaging their values up into a data structure, and that's the environment. In the interoperability semantics, we do essentially the same thing, but we rely on optimization. It turns out at runtime, there are no free variables, so we just generate the empty environment. We could do exactly the same thing as the compiler. Look at all the free variables, generate a data structure, but since at runtime, that's always empty, we just optimize that away. So you can see that these two rules are doing essentially the same thing. The interoperability semantics are generating a pack statement, generating closed code, generating an environment, and so is the compiler. But we've written them twice in slightly different ways, and now we have to prove their equivalent. This is very frustrating. And it turns out it's not necessary. So my observation is that instead what we can do is start from the interoperability semantics, these interoperability rules, and we can derive from them the compiler. And the idea here is that the interoperability rules form a reduction system, but that doesn't have to mean runtime. We can choose a different reduction strategy for these rules to derive the compiler. Now, to do this, these interoperability rules need to be more general than usual. For one, they need to be considering open terms, terms with free variables, so that we can translate all the terms in the language, not just the runtime terms. They also need to be triggered in an arbitrary context, so we can translate not only the top level of terms, but translate sub-expressions. Once we do this, we pick a different reduction strategy to derive a compiler. Essentially run all of these cross-language rules and don't run the source or target rule, and we get a compiler. And in fact, depending on the reduction strategy we choose, we get a different model of compilation. So we can derive many compilers from this one set rule. So for instance, if we choose to fully normalize all of these cross-language redexes, we get an ahead-of-time compiler. We just keep running these translations until there is no more source term left and we only have a target term. That's a compiler. If instead we non-deterministically run in the multi-language, either choosing to reduce a source term in the source semantics, or choosing to translate it to the target language and then run the target semantics, that models just-in-time compilation, at least without speculative optimization. So if we go back to our multi-language example, we have our source language and its source semantics, our target language is target semantics. We've defined the interoperability rules. Here's how we derive some compilers. So for an ahead-of-time compiler, I have this E1 in the source language that I want to translate. So I wrap it in a boundary. I tell it now needs to behave like a target term. And then I run only in the cross-language reduction system. I run all of the cross-language reductions until there are no more left. And that is a fully translated target term. If I want a different model, I want a JIT compiler, and I define a different reduction system. So in this one, if I have a source term, it can take a step in the source semantics. If I have a target term, it can take a step in the target semantics. Or if I have an arbitrary multi-language term, source or target, I can try to trigger one of these cross-language redexes on an arbitrary subterm. So I translate some sub-expression from source to target. Now, if I run these non-deterministically, I get a model of JIT compilation. I either am running the source interpreter, or I translate something and then I run in the target semantics. Now, beyond the lack of duplication, there are some additional benefits to modeling the compiler this way. We can reuse results about reduction systems to imply properties of the compilers. So the big one is confluence. It turns out that confluence implies compositional correctness and part of the full abstraction, the secure compilation theorem. So I'll walk through the similarities and sort of how the proof goes that confluence implies correctness, but you can find all the details in the paper. So here on the left, I have a whole program correctness theorem, and on the right, I have a confluence diagram for our multi-language semantics. So in a typical correctness theorem, we have something like we have our source program E, and it runs to a value in the source semantics. That's modeled in our confluence diagram by we start with the source term, and we take a step of evaluation in the source semantics. Our compiler is modeled as well. We have the source term E. It compiles fully to a target term E. In our confluence diagram, the source term we start with takes a step translating something to the target language. With compiler correctness, we want to know that the target E that we produce, evaluates to some value, and that's modeled in our confluence diagram by taking that red term and performing some target reductions. And of course, we want to know that we always get to the same place. So in the compiler correctness theorem, the two values we compute are the same or they're related in some way. And in our confluence diagram, whether we started by taking a source step or started by taking a cross-language step, we always get to the same target value in the end. Okay, so that's about all I want to say in this talk. In my extended abstract, I discuss a few more consequences and show the details of some of these proofs, but this is the basic idea. If we start from an operational semantics of our source and target language, then define a multi-language semantics, defining a slightly more general notion of interoperability over open terms in an arbitrary context, then we can easily derive not only a compiler, but multiple compilers. We can get the ahead-of-time compiler by fully normalizing cross-language reductions. We get a just-in-time compiler by just running non-deterministically in this multi-language reduction system. And by proving properties of this reduction system, we imply properties about all of these models of compilation. In particular, if we prove confluence, we imply compositional correctness of both of these compilers, and it also implies part of the secure compilation. Now, before I give you the impression that this solves all the problems, I'm not entirely sure. On the plus side, the technique does seem to scale, so I've modeled a compiler from a scheme-like language down to an assembly-like language. And there are other interesting corollaries, so other standard results about the reduction system that connect to the compilers. On the downside, confluence is not always an easy theorem to prove. And in fact, at least one technique I know for proving it essentially constructs a compiler from the reduction system and then proves compiler correctness. But I'm hopeful that this will actually be easier than proving compositional correctness or full abstraction. I'm also not sure if there are any other useful results about reduction systems that somehow connect to the compiler that this models, but I'm sort of hopeful there are. Okay, so that's all I have for this talk. You can find the extended abstract with lots more details at the link on the slide. If you're attending the synchronous section, please come, feel free to ask me questions. Otherwise, feel free to email me your questions. Thank you.